Thanks for the invitation for this workshop. I'm honored and privileged to be at Samsung and presenting our research in the area of silicon nanophotonics, which is the result of several years of works of my students, postdocs. Some of them are listed here. The topic that I would like to focus on, assuming a wide range of interest from audience, is the ability of silicon nanophotonics to make changes, and also the needs of this technology by itself to address the next generation devices and systems, and how this technology should move from silicon into something that we call hybrid materials. There are several advantages that make silicon very attractive for a lot of applications, including nanophotonics. Some of them listed here. It's a low-cost material. It's available on the silicon on insulated platform that makes confinement of light possible by contrast of index of refraction. It's reconfigurable, meaning that you can change its optical properties by different means. And most importantly, there is a big IC fabrication backbone thanks to CMOS technology that makes the fabrication of silicon at the high level possible for manufacturing. It's a natural material to integrate electronics with it, and we can densely integrate optical functionalities on a chip. So these are the main reasons that there has been a lot of investment in the silicon photonic technology. Just to name one recently, the $200 million investment of US government in forming foundry processes to make silicon photonic technology possible for manufacturing through AIM photonics. Nevertheless, silicon has its own shortcomings. For optics, it's an indirect bandgap material. We can't make lasers and LEDs and light sources in it, so we have to bring them from somewhere else, either off chip or bond them to the chip. That adds a level of complication. It has some absorption mechanisms through free carriers and so on that I say a few words about it. But at the first glance, we may say that silicon is a low-loss material optically. But when we get into pushing the limits, then we see that the loss of silicon starts to become prohibitive, and something has to be done. Silicon has nonlinear coefficient. This means if you increase the power of your optical beam into your structure, the nonlinear processes start to kick in, and you get unwanted results. So these are the shortcomings that I wanted to list. And there has been a lot of applications proposed, demonstrated, and some got even into products using silicon photonics. First and foremost, optical links and interconnects, board-to-board, chip-to-chip, on-chip. All of them have been the topic of discussion in silicon photonics. Optical computing, phased arrays, and LiDAR is now a very big application for silicon photonics. Several companies are investing on it. Sensing, from bio and chemical sensing for medical to hazard detection to environmental safety applications. And spectroscopy, just to name a few of these applications. This cartoon shows an example done in Japan of a link in an optical system where you have a laser diode array. You have an array of optical beams at different wavelengths. You modulate them using an array of modulators. You let them propagate on the system using your waveguides, and then eventually you do your photodetection. So technically you send the signal from modulator to the photodetector as a link on chip. Throughout the years, the optical interconnects have developed to address higher and higher bandwidths with larger and larger number of channels per centimeter squared, as shown here. And of course, the trend is always upward from things like rack-to-rack, board-to-board, and now chip-to-chip and on-chip. Now, looking at the numbers, we're looking into terabits per second per centimeter square, and then pushing without, assuming any limit for ourselves as the technology requires higher and higher and higher data rate and smaller and smaller feature sizes. So silicon photonics has the capability to be on the top in this technology. Now, there is a problem with this. I don't know why on this computer it happens, but I apologize for that. This is the trend in silicon photonics market forecast, and the market is really booming, and again, there is a lot of expectation in the years to come. Let me say a few more words about the optical interconnects. Well, the real challenge is very simple. We need to replace the copper wires into optical means of connection because we want higher speed. So that's the first glance on why optical interconnects are needed. This is a typical data center where all the orange cables show optical fibers, but at the same time, there is a major challenge, and that's the power consumption. So interconnection accounts for a large portion of power consumption. So there is a lot of push to make things faster and faster, at the same time, lower and lower in power consumption. These are some of the requirements that in interconnection and links are needed. We're pushing toward petabit per second per centimeter square, 10 to the 15, 1,000 terabit per second, something really aggressive, high capacity optical routers, and either data center or multi-processor chips, they would like to rely on optical means for that. And the key bottleneck that exists is the modulation, because that's where electronics meets optics. That's where your data, bits of 1 and 0, will go on an optical beam, either on a waveguide on a chip or on a fiber for rack to rack. That's where a lot of efforts is needed. And these are some of the properties for a modulator. You need to have operation voltages of less than a volt for operation. Power consumption, even for the near future, we're talking about 1 to 10 femtojoules per bit of modulation, while down the road, the power consumption goes into attojoules per bit. That's where the big thinkers for 10 years down the road are now focusing their energy to get into attojoules per bit. Speeds of greater than 50 gigahertz, or in the language of data rate, 50 times 200 gigabit per second. And then when you have such a modulation, then you can use multiple wavelengths using wavelength division multiplexing to have multiple channels going through the same link. So you just multiply this 100 gigabit per second by the number of channels to go to higher and higher data rates. And of course, when you use optics, optical routers have to be also wideband for channel switching, and there should be fast for packet switching. And this is an example of what people have envisioned in silicon. This is a complete silicon photonic interconnect fabricated using CMOS process at MIT. This is the version they published in 2015. There is another one published in 2018 where the performance measures are relatively similar. So that's where you have the modulation and then sending the signal on the same chip to your destination with the silicon germanium detectors. The key thing is that this is one of the best results published in silicon, but still large enhancement is needed in order to meet the future needs of interconnection. This is the best example of on-chip interconnect, where 2 points on the same chip are connected using optical means. Of course, alternative to silicon, there is 3-5. This is a great work at John Bauer's group at UCSB, where everything is done in 3-5 materials. Again, this is a 8 by 8 by 40 gigabit per second. And that's just kind of, the optical means are done through 3-5 semiconductors. Now, let me shift gear now with this motivation in mind that there are some bottlenecks in this technology, and modulator being one of the most important ones, and see what the community of silicon photonics have envisioned to address such needs. Well, of course, based on recent advances in silicon photonics, we are now in a position to hope that these challenges can be met in the next future. Some of these advances are, increasing the modulation speeds. Modulators of 100 gigabit per second data rate have been made possible. Integration of sources and detectors to silicon through bonding of 3-5 semiconductors and silicon. One of the most important improvements is the ability to fabricate waveguides and resonators as building blocks of integrated optics with ultra-low losses. That's really important in making structures that are low power, reasonable performance. And then using those waveguides and resonators, an array of high performance functional devices, couplers, filters, spectrometers have been fabricated. And then added to that, the recent investment in having foundry processes for manufacturing of such technology has been a big boost. Now AIM Photonics is there, Global Foundries is there. They are offering the dedicated integrated optic fabrication processes where now people can sit down on their cadence and design structures that have modulators, waveguides, and so on and so forth, and then have them fabricated at the foundry. Now, I would like to show some of our work in using resonance-based integrated optics. The reason resonators are very attractive is, one of the reasons at least, is that they save a lot of space, increase the efficiency. Optical wave usually propagates in a waveguide, but then alternatively it can go through a resonator and then go around the pad many times, depending on the quality factor of the resonator. So this reduces the size of propagation you need for your application considerably, going from centimeter waveguides all the way to 2-micron radius microdisk resonator. So that's a huge advantage. Typical resonator coupled to a waveguide at about 100 nanometer spacing show a transmission spectrum through the waveguide that has some dips, and each dip is the representation of one mode in the resonator where the signal is sucked into the resonator, and as a result you get very low transmission through the waveguide. By zooming in one of these and then looking at its bandwidth, we will define the quality factor. And the quality factors of a few million is about the record for a disk that is in the ballpark of 20 micron radius, just to have some numbers in mind for silicon. Of course, a structure like this has a lot of modes that, depending on your application, might be bothersome. So we invested in fabricating structures that are very small in size, rather than 20 micron, 1.5 micron. And now you can see that in a big range of wavelengths from 1500 to 1560 nanometer, you only have a single mode with quality factors in the ballpark of 100,000. You can have more than one waveguide and use that as a filter. This is an add-drop filter fabricated in this structure. Now, having a structure like a resonator that is small and only affect the spectral range in a very narrow line width gives us the ability to use an array of these resonators to perform the functionalities of interest. In this example, there are 6 resonators fabricated and coupled to the same waveguide, and you see that each resonator addresses a small portion of the spectrum. So by combining this array of resonators, you can simply form the transfer function or response over frequency that you are interested in, each one of them addressing a small bandwidth. So it gives you a lot of resolution. We can have resonators that are simple or resonators that are coupled that gives us a more flat band response. A natural application of this is a spectroscopy where each resonator is supposed to take the signal at a small channel of a spectrum, and then by combining multi-resonators, I can have different regions of a spectrum covered and monitored. This is an example of a 90-channel spectrometer in a 60 by 60 micron squared area. It provides about 1.1 nanometer resolution over 60 nanometer bandwidth, less than half a dB insertion loss. Just to put it into the prospect, a spectrometer with this performance, 0.1 nanometer resolution over 60 nanometer bandwidth, a conventional spectrometer is really expensive. But that's just a simple chip. Now, this is how the system is designed. What we have a waveguide that brings the signal in, and we have an array of resonators as shown here. Each resonator separates the signal and send it to a waveguide, and these arrays of waveguides are shown here, bring the signal to the center. I have half of my resonators here and half of my resonators there, and then I just interchange them one by one just to avoid crosstalk between adjacent resonators. And then in the center, I use an array of scatterers to send the signal off chip for me to analyze that. That's a simple design to be able to analyze the performance of a system. And that's the response. So this is the device under test. Light comes in, goes out, and then from the top, I monitor the light that is scattered out. So as I change the wavelength of input, I go from one resonator to the other, to the other, to the other. And then there are some apparent crosstalk. That's just because of the saturation of the detector. So this system is capable of providing a spectroscopy, 0.1 nanometer resolution over a large bandwidth. And what we really envision as the future use of that is that instead of an array of waveguide bringing the signals out, we put scatterers on top of each resonator, and then they send the light out directly. A detector array will be fabricated on top or bonded on the top through a lenslet array just to match the pixels. So you will have a very simple chip that provides such a large performance. Structures like that would be very important in sensing applications where a lot of detection is done in the spectral domain. Now, the next level of application relies on changing silicon to do something, what we call reconfiguration. Reconfiguration, in essence, means changing an optical property of silicon, either index of refraction or absorption, preferably index of refraction, because absorption means loss, loss means power, power means cost, and we are pushing for minimization of cost and power consumption. So any process should be CMOS compatible, low power, wide tuning range. It should be fast and low loss. And these are the methods that people have proposed for silicon. Either inject carriers in silicon to change its index of refraction, heat it up, apply a voltage and infiltrate a polymer. That polymer works with the voltage to change the index of refraction, or use optomechanical tuning. So these are some examples of this tuning mechanism. This is an example of a filter architecture where the filter unit cell is shown over here. It's an array of waveguides and resonators. And each unit cell provides a second order filter for you. By combining multi-second order filters, you get a high order filter. And then by changing the properties of silicon, you change the functionality of your filter. This is an example of fabricated structure. It's a fourth order filter that we fabricated at Georgia Tech. The key thing is that by applying heat through electronic means, you will change the functionality of the system. This is the same filter under two different inputs. It has a notch response or band reject response, and you change the wavelength that it operates at. The same filter structure under different set of input control signals will act as a bandpass filter, in which you have the control over the center wavelength and also the bandwidth. So it's a kind of a multi-purpose filter chip where you only change the control signals. And based on that control signals, it gives you a different functionality. Potentially, it can operate at, about with thermal heating, about 100 nanosecond reconfiguration time. So it's really fast for a lot of application where you want to sweep the spectrum and monitor the spectral content. Well, if silicon is so good, then why should we go for hybrid materials? Well, silicon is good, but it has its own problems, as I mentioned. Limited power handling due to nonlinearity, limited quality factor due to absorption. So resonators in silicon cannot be made more, more effective. There are also fabrication-induced randomness in the structures. You form a resonator to be 2 micron in radius, you get a few nanometer error over that micron. That few nanometer error, because of fabrication, will shift the resonance wavelength. It doesn't operate at the wavelength you want. So you have to come back and somehow correct it. So that's another problem that exists for many materials. And then, thermo-optic, based devices are very good for also correcting the wavelengths of a resonator by putting a heater on the top, but usually they are power consuming and also they are low speed. That has motivated research on silicon nitride over the last decade at least. And the reason is silicon nitride has much less nonlinearity and also very low absorption because it's technically a dielectric material. So there has been a lot of effort in making high quality silicon nitride devices. This is an example of a fabrication process we developed where you can get very good sidewall with very low amount of roughness. This is a mask that is used, a flowable oxide mask on top of silicon nitride, which eventually will be removed by wet etching. But using that type of process, quality factors in the range of tens of millions have been achieved in silicon nitride. So that's one order magnitude improvement. This is an example of a silicon nitride a structure that even can be fabricated on top of silicon if needed. Quality factors of 8 million and 16 million for different radii have been achieved. The problem with silicon nitride is that it cannot be tuned. There is no reliable, efficient tuning mechanism to change its index of refraction. So now we have a material that is ultra low loss, perfect for a lot of application. We have a material that is tunable, silicon, that is not ultra low loss. And of course, the natural way of thinking is to somehow combine the two, if we can, to just marry the advantages of the two. So that brings the general concept of hybrid material platform, where you basically have a multi-layer structure, which over different regions of the chip, you will have different sets of materials. Silicon and silicon nitride, I justified their importance. Each one of them addresses a portion of the needs. Things like graphene, metallic structures if needed for plasmonics, and so on and so forth. So that's the general concept of hybrid material, where different layers of material provide different functionalities that other materials cannot, and then you just send the light between different layers whenever needed for application. So that brings a lot of new problems, from developing a reliable process for a material that is not lossy, it's low loss. I mean, all the surface tensions and stresses between materials, quality at the fabrication, and so on needs to be studied. And also, you should send your light whenever you want with high efficiency between different layers. So that's what we have been working in the last at least 7-8 years. The first material that we developed is a double-layer silicon. Now, the way it works is that you have silicon on insulator that you purchase, you grow thin layers of oxide on the top of the two, and then you bond them together through a sophisticated bonding process, and then you etch away the top silicon and the top oxide layers. So now what you end up getting is a double-layer silicon with an oxide in between, as shown over here, oxide in the middle. This is a waveguide, and this is a resonator. Now, to see the quality of this structure, we usually fabricate resonators and measure the quality factor and compare it with what we can achieve in the same silicon material, not double-layer, single-layer. So here in this example is a miniaturized resonator with quality factor of about 60,000, and this is a 20-micron microdisc quality factor of about 600,000, very similar in the ballpark to silicon. And we were able to, kind of perfect this technology to the level, as you see, a comparison with other published results show that, in radiuses of 20 micron, we get quality factor of 500,000, and 5 micron will give us 250,000, just comparing 200 micron 42K, and so on and so forth. So in essence, I think the take-home message is that it's possible to make multi-layer materials at very high quality, but what's the motivation behind this technology? Where one of the main reasons for this technology is the challenge of reducing the power consumption and being able to have a reliable process to correct the errors in the fabrication or errors caused by fabrication in the resonance wavelength of our resonator. So the way this device works is different from conventional silicon. In conventional silicon, you have one layer, and you have to inject or deplete carriers by a p-n junction. This is nothing but a capacitor. Silicon, and oxide is a capacitor. So we apply the voltage between the two silicon layers, and then we have charges in them, and this results in the shift in the index of refraction without requiring a current. That's what a p-n junction has to do. Reducing the current will considerably reduce the power consumption. That's one. Number two, if a resonator is fabricated and it has resonance shift due to fabrication imperfection, I add a DC bias to that. That just corrects that fabrication imperfection. So that's a technology that uses hybrid material to push for reduction of power consumption. And then there is a lot of games that we can play, because now the capacitance here defines the voltage of operation, because you need so much charges to be accumulated. The larger the capacitance is, the smaller the voltage is. Q equals C times V. But then at the same time, when capacitance is large, your speed is sacrificed, because RC time constant is your speed. So these are the type of trade-offs that we deal with in this technology. And just to move ahead of myself, I mean, eventually, if we use a very low resistivity material like graphene, then I wouldn't worry about resistance, and I can play just with the capacitance. So that's kind of a trend that it opens up as a new hybrid material platform. This is the example of applying different voltages to a resonator, and then you will see that the resonance wavelength just shifts by applying the voltage as we expect. Index of refraction shifts. So this is the actual a structure for fabrication. I didn't get too much into the detail because I assume people are not very interested in the deep technicals. But just to tell you, always we have a challenge of putting contacts in optical structures because metal means loss. And we don't want metal to see our electromagnetic fields. So here, the two contacts is placed one in the middle of the resonator. The electromagnetic field of the mode is usually in the periphery. It doesn't see the center of the disk. So I can safely put one electrode there, and then I will keep my silicon about 30 nanometer or so around the structure as a pedestal. Electromagnetic field doesn't get into that, so I will put my second contact there. So this way, I'll just make sure that the contacts don't add loss. Some of the SEMs are shown over here, waveguide and resonator at the coupling region. And this is the type of problems that we always study in these structures. So we have a resistance here. We have a resistance here where voltage is applied, but the signal has to get into the center. Capacitances are there, so we try to kill the unwanted capacitance, minimize these resistances by doping these regions, and then try to maximize the speed through that. This is the actual device under DC, so you can tell that by applying a voltage, you accumulate the charges, but you want your charges to be electrons and holes, not donors and acceptors. So you have to pick the correct polarity. If this is p-type, this should be p, this should be n, positive and negative. This is holes, this is electrons, and that's why you will get a better sensitivity compared to the case where you apply the voltage in the reverse direction where some of the donors and acceptors help you. But that's just trivial things in this type of structures. This is the measurement setup, just in case you're interested in the type of experimentation that we do. The essence of it is very simple. You have a device under test. Light comes in, goes out through fiber and fiber. So fiber couples to waveguide, gets the signal from the waveguide. This way, we have a laser that has polarization controller because the devices are polarized. And then the output goes amplified and then goes through different monitoring processes where you can use optical power monitor, you can use oscilloscope, a spectrum analyzer, bit error rate tester, and so on and so forth. But in essence, light goes in, light comes out. That's about it. And this is the performance of such a device, such a modulator, where you will monitor the response as the frequency changes. We're limited to some degree by our characterization tool, but this can easily get to 15 gigahertz. Eye diagrams and some of the performance measures, bit rate of 30 gigabit per second at 55 femtojoule per bit power consumption. The new designs are working at 27 femtojoule per bit and 60 gigabit per second. As you can see, the speed is there. I mean, 50 gigabit per second per channel is pretty good, even though the push is 400 in the next generation. The power consumption still needs to be improved. I mean, that's the typical power consumption today, but still there is a lot to be done in these type of structures. Now, to reduce the power and push for the applications that are looking for higher speed, lower power, then at some point we have to somehow augment silicon with a low-loss material. That's the next material that we develop. It's silicon on silicon nitride material platform. So the way it works is that we grow silicon nitride on top of an oxide, and this is a silicon on insulator, and then we grow oxide on the top of the two structures and then bond them together. And then after bonding, we get rid of the top silicon and the top oxide. We have silicon on nitride. Specifically, we need to grow some channels for degassing. When we bond them, air bubbles form, as shown over here. And when you have degassing channels at very large distances, 500 micrometers, that is avoided. You have a lot of devices you can fabricate in this tiny region. This is the example of the fabrication process. So we usually fabricate devices using lithography, in our case, electron beam lithography, and etching, which is dry etching, typically using inductively coupled plasma etchers. And then after fabricating the device in silicon, we fabricate the devices in nitride, and that's an example of a fabricated device. Now, to show the potentials of this technology, we go from the top using a grating that is shown over here. Light goes into silicon. We taper silicon down to 50 nanometer. That automatically pushes the signal into a nitride waveguide underneath with better than 97% efficiency. And then the signal goes into nitride, couples into the resonator in the nitride, and then it comes back to silicon, comes back to grating, and comes back up. This is the transmission spectrum of the device. As you can tell, the loss over a big range is very minimal. That means we have very high efficiency coupling between the two structures, and the quality factors of a few million have been demonstrated, showing the good quality of the material. Now, this material platform was developed to address a big challenge in modulation. As I said, pushing toward speed at lower power. Now, just to get into that modulation technology, I have a very simple cartoon that I like to show. So in conventional modulation that I show, we typically change the refractive index of this material, and the resonance wavelength shifts, and as a result, signal goes from high to low, or vice versa, in the waveguide, which is bits 1 and 0. That's how modulation is done. The problem really is that if you make a very high Q, a very sharp resonator, a little change in its wavelength is enough for doing the modulation. But then a high quality modulator has a long photon lifetime, meaning that optical beam stays there for a long time, and you have to wait until that is emptied up in order for the next bit to be modulated. Just to think about a simple example, suppose you have a dam and then you want some water in a channel. So in one idea, you just empty the dam and fill it up again for each bit of water in the channel. That's what we do in here. We fill up the resonator with photons. That's called resonance. We just empty it up. That means off resonance. And we have to wait for this emptying up to be done. So that's why in technology, usually we use lower Q resonators in order to have our data rate at tens of gigabit per second. So we can't take advantage of the sensitivity it gives us. Now, in the second example, what we do is we don't touch the resonator. It's a fixed resonance. All we do, we change the coupling of light from waveguide to resonator by a small amount, meaning that in that dam example, I just bring the wall down a little bit and up a little bit. So I don't empty my dam. I just bring it down and up for enough signal or enough water to get into my channel. Remember that the signal in the resonator is thousands of times larger than that in the waveguide because it develops over time. So all I need is just a tiny change in the coupling coefficient in order to get my modulation. This way, we break the trade-off between power consumption and speed. So in order to implement this, and I'm not going to get into the details of the formulation, only mentioning that this curve tells us that if the quality factor is higher, then the change that I make in the coupling coefficient is lower to get from maximum to 0 transmission, bit 1 and 0. So higher Qs are preferred. That's why nitride is preferred, because it gives me Qs of tens of millions. Now, in order to implement that coupling, this is the actual design that we have. So this is a resonator in silicon nitride, and then we have two waveguides. So this is just one waveguide coupled at 2 points to that. So what happens here is that I play with the waveguide in between. I add a phase using my modulating signal, my RF signal, so that the interference of these two either constructively or distractively add up. This way, I get modulation done. And these are the two cases where you can see that by just changing that phase, you can go from top to bottom in transmission. Now, this way, the amount of phase shift that I need to get to 0 from maximum is, pi over 20, pi over 200, depending on the quality factor of that resonator. This is the actual device that we fabricated. This is the resonator in nitride and the waveguide in silicon, pads for applying the signal with PN junctions. And this is the response of the system. Just first to try the performance, we just heat it a little bit. Heating changes the index of refraction. By heating the device a little bit, we go from 0 transmission all the way to very high transmission. So that's the typical performance. And this is the actual transfer characteristic and the eye diagram of the device. Just to mention a few things. Number one, this is a high Q resonator. Lifetime of the cavity will tell us that, if it was conventional, it would work at 1 gigahertz, nothing more than that. This easily works at 12 gigahertz without a problem. Bit error rate of 9 times 10 to the minus 4 is achieved by, at 10 gigabit per second. And the insertion loss is only 3 to 5 dB. So that type of a structure is now being worked on getting into 60 gigabit per second at a few femtojoule per bit power consumption. And that's the direct result of using a hybrid material that allows me to combine a very high Q device or very low loss material with an integrable material. Now, in the rest of the slides, I just show you quickly where we get from here. In order to marry the two technologies I showed you, we need something that has double layer silicon in order to minimize the power consumption over silicon nitride. So the same technology, but rather than using one layer of silicon, I use 2 layers of silicon as a capacitor to do that. And of course, we have developed this bonding technology. This is the SEM of the bonded material. So now we are working on making devices in it. This shows again, the quality of the material is tested by fabricating a resonator and measuring its quality factor, coupling the light by tapering the waveguide. And again, we will get very high quality factors, a few million again. And that's where we are right now. We are now looking into improving the performance of this device. Basically, this is double layer silicon, and then this is nitride, so resonators should be fabricated here, and then modulation should be done over here in a waveguide. We are also looking into etching the oxide underneath and infiltrating it with polymer. This is a crude example of first trial. And then using polymers will allow us to apply a voltage and use electro-optic effect in polymer, which is very fast and sensitive. So that opens up a lot of capabilities. For those who might be interested in quantum effects and nonlinear optics, silicon carbide is a very good material, better than silicon and silicon nitride. Vacancies in silicon carbide will act as quantum sites. And again, we have developed silicon carbide on silicon platform that shows over here. Now, typically, when you grow silicon carbide on silicon, the problem that you face, the problem that you face is that the bottom surface of carbide has a lot of defects and problems in it because of the mismatch that exists between the two materials. So that has hindered the integrated photonic devices that utilize silicon carbide. So what we work with is a bonding process where technically we grow a layer of oxide that is thick enough that doesn't let light to see silicon underneath, and then we bond this silicon carbide on silicon on top of my oxide. By removing silicon by etching, I get access to the top layer, which is the culprit in a lot of experiments. That's the very low quality. So I kind of reverse this material and then get rid of silicon. I access to this side, and then we do chemical mechanical polishing on that in order to bring the quality up. So that's the original sample. As you can see, the top layer of the original sample is very good. That's where we bond and bring the bottom layer up. That's very terrible. These are AFM that shows the surface roughness. And then after chemical mechanical polishing, we get much better performance. Using that, we fabricate the structures in the silicon carbide on oxide, and then we use grating for coupling and so on. And this is the result of the quality factor of these resonators. This is the transmission through that waveguide, and the dip shows the resonance mode. And by focusing on each resonance mode, we can get quality factors. And this is the highest reported today. So we can bring quantum features to the chip if we want, thanks to silicon carbide. This is the very high speed devices that we have envisioned using 2 layers of graphene on top of nitride. So that's the same capacitor we talked about in silicon. Only difference is that we take advantage of the very low resistance of graphene in order to bring the speed high. And this is a flavor of other materials that we have worked with. We're working with 2-dimensional materials, mostly transition metal dichalcogenides. These are direct semiconductors. That's where the active functionality in silicon is missing. So that's 2D material on top of silicon nitride in this example. Infiltration of slots in devices with polymers. Electro-optic polymers bring electro-optic effect with very good speed and high sensitivity. And these are, different versions of the double layer silicon on oxide and carbide. And still there is a lot to be done. We are working for some very low power application on lithium niobate and silicon nitride. And at the end of the day, I think the take-home message really is that silicon is great. It has shown a lot of promise and has brought us to this point. Now, like any other technology, the next leap requires augmenting silicon before deciding to drop silicon. And this augmentation of performance is done by using hybrid materials, where depending on the application, we either bring the very low loss feature, we bring the quantum feature, or bring the active feature. But the name of the game really that pushes my group at least into this direction is the ability to form devices, especially modulators and switches for interconnections that can enable using WDM terabits per second, and lower than femtojoule per bit power consumption, something that cannot be envisioned with silicon. And with that, I'd like to conclude by thanking the funding agencies that supported this research, and of course, all the students and postdocs in my group. And thank you for your attention.
I'm a semiconductor process guy. So the geometry is basically 20 micron, something like that.
The geometry of
Yes,
what?
of the fabrication
Resonators?
process, yes.
Well, the resonators are usually somewhere between 1.5 to 2 micron is in radius. They could go all the way to 100 micron if we want to really push the quality factor.
So for the CMOS circuits, so the geometry is what? Is a sub-micron or? For the circuits.
The
For the
electronics?
electrical circuit, CMOS, right? You're talking about trying to utilize the CMOS.
Eventually,
process, right?
yes, yep.
So
These are
what's the normal-
fabricated using electron beam lithography and etching at our clean room.
Yeah, I'm trying to understand.
Yeah.
What's the geometry of the CMOS for electrical circuits?
Well, if you're talking about the technology, currently the 90 nanometer technology is being used at global foundries, and they are pushing for 45 nanometer technology in the near future for fabricating integrated photonics. That's correct.
Good enough. Thank you.